just gonna take 2 cups of water. And put it in the blender. Okay, maybe I'll do another 1/2 cup. Okay, and then I'm going to take about 3 leaves of cabbage. This is red cabbage. Just gonna tear these up a little bit. Do one more. Alright, and then I'm gonna screw on the top. Okay, now I'm gonna blend the mixture so that we get a nice cabbagey solution. Okay, so as you can see, the water is like really purple now. Okay, so I've put a coffee filter in this steamer basket with holes in it so that I can make a filtrate that only contains the liquid from the cabbage water and not any of the actual leaves. I almost opened it the wrong way. Okay, so now I'm just gonna continue pouring the liquid over. You see the filters there, so no cabbage leaves are gonna get out. It's just the liquid. And as you can see, with just water mixed with the cabbage, the color is like a bright, pretty vibrant purple color. So assuming the water has like a pH of 7, we can assume that at neutral pH, the cabbage is purple. Okay, so now it's done filtering, so you can see that what's left in the coffee filter is all the solid bits of cabbage that didn't make it past, and then put that in the sink. And then here we just have left some pretty purple cabbage juice. So I'm gonna take a cup and I'm gonna evenly distribute the cabbage juice to all 3 jars I have here. So just about 1 scoop for each of them. And then I'm just going to repeat that until there's no more liquid left in the bowl. And then this one looks like it has a little less, so I'm just going to pour some in there. It doesn't have to be exact because we're just looking for a color change. Okay, so now our 3 jars have cabbage juice, and you can see under neutral pH it's all purple. So first we're going to test how the cabbage juice changes in response to an acid. So I have some vinegar here, which is acetic acid. So I'm going to open that, and I'm going to add just 1 tablespoon to the acidic jar, and we're going to see if the color changes. Wow, so you can see that it's turning pink, and I'm going to get a spoon to stir it with so that we can really see. And it smells like vinegar. So I'm just going to add 1 more tablespoon to see if we can get it more pink. So as you can see, upon addition of an acidic liquid to the jar, the pH of the liquid decreased because there's an increase in the concentration of H+ ions, and that chemical change was enough to change the color absorbed and transmitted by the liquid. Okay, so now we have our jar for the base, and I have some baking soda, which is kind of a classic base, so I'm gonna pour about I don't think I'll need a tablespoon. I'm gonna do about half a tablespoon to start. It's kind of hard to get it out. All right, so we have about a half tablespoon. I'm just gonna add that. And you can see it's starting to turn from purple to blue. Wow. You can see it's really blue now. I'm just gonna add a little more to see if we can get it to change a little more. I'm just gonna pour it directly in. So when a base is added, the concentration of hydroxyl OH minus ions increases, meaning the pH increases as well. So that means that increasing the pH changes the color of the liquid from purple to blue, and decreasing the pH changes the color of the liquid from purple to pink. So the compounds that are responsible for giving red cabbage its color are called anthocyanins, which are a member of the flavonoid family. Flavonoids all contain two phenyl rings connected by a heterocycle, and they have a highly conjugated structure, which makes them stable enough to absorb and transmit visible light. So how does this happen? Different wavelengths of light are associated with different energies. Light of a longer wavelength is associated with lower energy than light of a shorter wavelength. Light of sufficient energy can be absorbed by a molecule, and when this happens, an electron will be promoted from a ground state to an excited state. On a molecular level, this means that an electron will go from existing in a pi bonding orbital to a pi antibonding orbital. The amount of energy needed to promote an electron from its ground state to its excited state depends on the energy difference between the bonding and antibonding orbitals. Electron delocalization raises the energy level of the bonding orbital and lowers the energy of the antibonding orbital, thus decreasing the energy difference between the two. This means light of a lower energy and longer wavelength can excite an electron on that molecule. As the extent of electron delocalization within a molecule increases, so does the wavelength of light it is able to absorb. Let's apply this to anthocyanin. The structure of anthocyanin changes in response to the pH of its environment. Under acidic conditions, anthocyanin exists as a flavillum ion, which has an unstable positive charge on the oxygen atom of the heterocycle. Protonation also makes it so that less resonance structures are available to the molecule, so the energy difference between the ground state and the excited state is relatively large. However, when the molecule is deprotonated, which occurs as the pH reaches approximately 7, the positive charge on the oxygen atom goes away, and as you can see, many more resonance structures become available to the molecule. This increase in electron delocalization decreases the energy difference between the ground state and the excited state and makes it so that light of a longer wavelength can be absorbed. Finally, at basic pH levels, the molecule will get deprotonated again, which makes it absorb light at an even longer wavelength because now there is an extra lone pair of electrons on the oxygen that can be further delocalized into the rings. The light reflected by a molecule is the complement of the light it absorbs. So, under acidic pH conditions, anthocyanin appears red because it is absorbing green light. Under neutral conditions, the molecule appears purple because it is absorbing yellow light, which has a longer wavelength than green light. Finally, under basic pH conditions, the molecule appears blue because it is absorbing orange light, which has a longer wavelength than both green and yellow light.